There is a number that planetary scientists use when they want to describe how Earth-like a planet is. It is called the Earth Similarity Index. It runs from 0 to 1. 0 means nothing in common. 1 means identical. Earth itself scores a 1 by definition. Mars scores around 0.64. Venus, despite being nearly the same size as Earth, scores around 0.44 because of what its atmosphere became. The highest score ever recorded for a confirmed exoplanet sits somewhere around 0.84 to 0.87, depending on which dataset you use and which assumptions you build into the calculation. We have never found a planet that scores higher than that. We have found thousands of planets. Thousands. And the closest any of them gets to Earth on this scale is 0.87. Now ask a different question. What happens if tomorrow that changes? What if we found a planet that scored 0.99? What if we found something that, by every measurable parameter available to modern astronomy, was essentially Earth? Same size, same gravity, same distance from its star, same atmospheric pressure, same temperature range, liquid water on the surface, a star nearly identical to the Sun. What do we do with that? Tonight, we are not going to answer that question the easy way. We are not going to talk about rocket ships and colonization timelines and how many generations it would take to get there. Those conversations happen. They are worth having, but they skip something more fundamental. The discovery itself, what it would actually mean scientifically, philosophically, practically, what it would do to the way we understand our place in the universe, what it would force us to confront about what we are and what we have done to the planet we already have. If this is what you come here for, subscribe. What follows is worth the time. Before we can understand what finding a perfect Earth would mean, we need to understand what finding any Earth-like planet actually requires. Because the popular image of exoplanet discovery, a telescope pointed at the sky, revealing a blue marble orbiting a distant star, does not match how the science works. We cannot see exoplanets directly, not the small rocky ones. The light from a star overwhelms the reflected light from any planet orbiting it, the way the sun's glare overwhelms the light reflected off Earth. If you were looking at our solar system from a nearby star, Earth would be invisible against the solar glare. You would need an instrument capable of blocking out the star's light with extraordinary precision and sensitivity to detect the faint smudge of a rocky world beside it. That technology exists in prototype form. Coronagraphs on the Hubble Space Telescope and the James Webb Space Telescope can block starlight to reveal features nearby. Future missions like the proposed Habitable Worlds Observatory, which NASA's most recent planetary science decadal survey ranked as a top priority, are being designed specifically to image Earth-like planets around nearby stars. But they do not exist in operational form yet. We are years to decades away from routinely imaging rocky planets in habitable zones. What we can do right now is detect exoplanets indirectly, through two primary methods, the transit method and the radial velocity method. The transit method works by watching a star's brightness over time. When a planet passes between us and the star, it blocks a tiny fraction of the star's light. The brightness dips by a measurable amount. The depth of the dip tells you the planet's size relative to the star. The timing of repeated dips tells you the orbital period. From the orbital period and the star's mass, you can calculate the planet's distance from its star. This is how most confirmed exoplanets have been discovered. NASA's Kepler mission found over 2,600 confirmed planets this way, by staring at a patch of sky containing around 150,000 stars for 4 years. The radial velocity method works differently. As a planet orbits a star, both bodies actually orbit their common center of mass. The star wobbles slightly. As it wobbles toward us, its light shifts very slightly toward the blue end of the spectrum. As it wobbles away, the shift is toward the red. This Doppler effect is measurable with sensitive spectrographs. The wobble amplitude tells you the planet's minimum mass. Combined with transit data, you get a complete picture of size and mass, which gives you density, which tells you whether the planet is rocky or gassy. These methods have limits. Transit detection works best for planets with short orbital periods because you need to observe multiple transits to confirm a detection. A planet with a 1-year orbit requires at least 3 years of observation to confirm. A planet orbiting at Earth's distance from a Sun-like star, the exact configuration we care about most, requires patient, sustained monitoring. Radial velocity detection of an Earth-mass planet in an Earth-like orbit around a Sun-like star is at the very edge of current instrument sensitivity. The wobble Earth induces on the Sun is about 9 centimeters per second. Our best current spectrographs can measure about 30 centimeters per second reliably. The next generation, instruments like Espresso on the Very Large Telescope and future-planned spectrographs, are pushing toward that limit. So when I say, we found a perfect Earth tomorrow, I mean something specific. We found a planet transiting a nearby Sun-like star, confirmed by radial velocity measurements that pin down its mass, with a calculated density consistent with a rocky composition, orbiting at exactly the right distance for liquid water, around a star stable enough to support a temperate climate over billions of years. That combination, confirmed by multiple independent measurements, would be an extraordinary discovery. But it would also be just the beginning of the questions. The first question anyone would ask is whether it has an atmosphere, because a rocky planet at the right distance from the right star is necessary, but not sufficient. Mars is at a distance where liquid water could theoretically exist on its surface. Mars does not have liquid water on its surface because its atmosphere is too thin to maintain the pressure and temperature required. A bare rock at Earth's distance from the Sun would be frozen and airless. We cannot yet detect the atmosphere of a rocky planet in an Earth-like orbit directly, but we are developing the tools. The James Webb Space Telescope can analyze the atmospheres of larger planets by observing how starlight filters through the atmosphere during a transit. The light changes in specific ways depending on which molecules are present. Oxygen absorbs at certain wavelengths, water vapor at others, carbon dioxide at others. This is called transmission spectroscopy, and it has already been used to characterize the atmospheres of gas giants and super-Earths. Rocky planets in habitable zones are harder because they are smaller and their atmospheres thinner, but the technique is in principle applicable. Webb has already produced atmospheric measurements of planets orbiting smaller, cooler stars called M-dwarfs, where the planet-to-star size ratio is more favorable. TRAPPIST-1e, one of several potentially habitable planets orbiting a nearby M-dwarf, has been analyzed by Webb with the goal of detecting atmospheric signatures. The results are still being interpreted. The science is being done right now. For a perfect Earth orbiting a Sun-like star, the atmospheric analysis would be harder. Sun-like stars are brighter and larger, making the planet-to-star ratio less favorable. We would need the Habitable Worlds Observatory, or something equivalent, to confidently characterize such an atmosphere. But say we did it. Say we measured the spectrum of light, passing through this planet's atmosphere and found nitrogen, oxygen, water vapor, carbon dioxide in trace amounts. A composition essentially identical to Earth's pre-industrial atmosphere. What would that tell us? It would tell us the planet has photosynthesis. Oxygen is chemically reactive. In the absence of a continuous source, it would combine with surface rocks and disappear from the atmosphere within a few million years. The only known mechanism for maintaining high atmospheric oxygen concentrations on the timescale of a planet's lifetime is biological photosynthesis. Plants, algae, and cyanobacteria split water molecules using sunlight and release oxygen as a byproduct. They have been doing this on Earth for roughly 2.4 billion years, progressively oxygenating an atmosphere that was once predominantly nitrogen and carbon dioxide. Finding high oxygen concentrations on another planet would not be Think about what we currently believe about the universe. We believe that life emerged on Earth approximately 3.8 billion years ago, from chemistry, from the interaction of organic molecules in the early oceans, under conditions that remain debated but were broadly understood to favor the formation of self-replicating molecules. We believe that this transition from chemistry to biology happened once, here, and we are the only confirmed example we have. The philosophical and practical implications of that belief, being wrong, of life having emerged independently on another world around another star, are enormous. It means that life is not a cosmic accident. It means that the conditions that produced life on Earth are not uniquely favorable to this one location. It means that the universe is, in some meaningful sense, biologically active. The Drake equation, which attempts to estimate the number of communicating civilizations in the galaxy, has one term called the fraction of planets where life arises, given suitable conditions. We currently have essentially no empirical constraint on that number. It could be nearly 1, meaning life arises almost wherever conditions allow. It could be nearly 0, meaning life is extraordinarily rare even given favorable conditions. We do not know. Finding a planet with biosignatures would constrain that number dramatically. If life arose independently twice in the same galaxy, the statistical implication is that life is common wherever conditions are suitable. That is not a small update to human understanding. That is a revolution. Now step back from the atmosphere question for a moment and consider something harder. What if the atmosphere showed not just oxygen and water, but something else? What if it showed nitrous oxide, methane, and industrial pollutants in concentrations consistent not with biology alone, but with industrial civilization? This is not a purely hypothetical scenario. Certain combinations of gases are difficult to explain without technological activity. The simultaneous presence of nitrogen dioxide, a byproduct of internal combustion and industrial processes, alongside other industrial signatures would be extraordinary. We may not be able to detect these signatures at the required sensitivity for decades. But the possibility is worth considering because it changes the question entirely. A planet with photosynthetic life is profound. A planet with technological civilization is something else. It means we are not unique as a type. It means the emergence of intelligence and technology from biological evolution is not a singular, improbable accident restricted to one lineage on one world. It means we are one instance of something that happens. That realization would land differently depending on what else the spectrum showed. If the industrial signatures were stable, unchanging over years of observation, it might suggest a civilization in a long-term equilibrium with its planet, something our own civilization has not achieved. If the signatures were changing, increasing in some compounds and decreasing in others, it might suggest a civilization in transition, possibly the way Earth's own atmospheric composition has been changing since the Industrial Revolution. And if the signatures showed high carbon dioxide concentrations alongside other industrial markers, it might suggest a civilization doing exactly what we are doing. Burning fossil fuels, destabilizing its atmosphere, warming its planet. We would be looking at a mirror. That possibility has a specific psychological and political weight that is worth sitting with. Imagine the discovery being announced. Imagine the press conferences, the journal papers, the public response. A perfect Earth orbiting a nearby star. Biosignatures confirmed. Industrial signatures detected. Carbon dioxide at levels consistent with intense fossil fuel combustion. The conversation about climate change on Earth would never be the same. The argument that human industrial activity is exceptional, unprecedented, unlikely to cause catastrophic harm because nothing like this has ever happened before, would be confronted by direct evidence that it has happened somewhere else, that whatever process causes technological civilizations to emerge also causes them, at some stage, to alter their atmospheric chemistry in ways detectable from light years away. We would not know the outcome for that other civilization. The light we are seeing left that planet years ago, decades, centuries depending on the distance. We would not know whether the civilization survived its industrial period, whether it transitioned to sustainable energy, whether it collapsed, whether it is still there. We would be seeing a snapshot of a process without knowing the ending. That uncertainty would be one of the most important pieces of information we have ever obtained about our own situation. Let us talk about the distance, because the distance is everything. The nearest star to the Sun is Proxima Centauri, about 4.24 light-years away. A light-year is the distance light travels in 1 year, traveling at 186,000 miles per second. 4.24 light-years is approximately 25 trillion miles. The fastest spacecraft humanity has ever launched. The Parker Solar Probe, at its closest approach to the Sun, reaches about 430,000 miles per hour. At that speed, reaching Proxima Centauri would take roughly 6,300 years. Proxima Centauri has a planet in its habitable zone. Proxima b, it was confirmed in 2016. It is roughly Earth mass. It orbits at a distance that would put liquid water on its surface if it has the right kind of atmosphere. But Proxima Centauri is an M-dwarf, a red dwarf star, and M-dwarfs present significant challenges for habitability because they produce intense stellar flares, and because planets close enough to be in the habitable zone are likely tidally locked, meaning one side always faces the star and the other is in permanent darkness. A perfect Earth around a Sun-like star would almost certainly not be at 4.24 light-years. The nearest Sun-like stars are farther. Alpha Centauri A and B, part of the same system as Proxima, are roughly 4.37 light-years away. Alpha Centauri A is the most Sun-like star in the immediate neighborhood. No confirmed Earth-like planet has been found there yet, though searches are ongoing. More likely, a perfect Earth around a true solar analog would be at distances of 10, 20, 50 light-years or more. At the current speed of our fastest probes, 20 light-years translates to roughly 30,000 years of travel time. At 50 light-years, it approaches 75,000 years. These numbers are not engineering challenges waiting to be solved. They are physical realities that constrain what interstellar travel can mean in practice. The concepts we use to make interstellar distances feel manageable: generation ships, cryosleep, fusion drives, laser sails, all of them face either fundamental physical limits or engineering challenges of a scale we have never approached. The generation ship concept deserves specific attention because it is the most scientifically grounded of the options. The idea is that a spacecraft large enough to support a self-sustaining population is launched toward the target, with the expectation that the people who arrive will be many generations removed from the people who departed. The voyage itself becomes a multi-generational civilization in transit. The challenges are severe. The ship needs to maintain a closed ecosystem for thousands of years. It needs to generate power without resupply. It needs to sustain not just physical health, but psychological health, social structure and cultural continuity across generations who had no choice in joining the voyage. It needs to decelerate at the destination, which requires as much energy as the acceleration. The genetic diversity needed to avoid inbreeding depression over many generations requires either a very large founding population or cryogenically stored genetic material. None of these problems are impossible in principle, but solving them requires a level of technological and social sophistication that does not currently exist. And the energy required to accelerate any meaningful mass to even a small fraction of the speed of light is extraordinary. Reaching 10% of the speed of light, which would allow a 20 light-year journey in 200 years rather than 30,000, would require energy roughly equivalent to the current global energy consumption of Earth for thousands of years to accelerate a single, modestly sized spacecraft. The physics is not sympathetic. What this means is that even in the most optimistic engineering scenarios, the response to finding a perfect Earth would unfold on timescales measured in centuries or millennia. There would be no emergency evacuation. There would be no backup plan that would save any individual alive today, or any individual alive for many generations to come. The knowledge that a perfect Earth exists would be exactly that, knowledge without the immediate practical ability to reach it. That disconnect between the discovery and any meaningful ability to act on it is psychologically significant. We would know it is there. We would not be able to go there. And the planet we are on, the one we have spent 2 centuries destabilizing through industrial activity, would still be our only option for survival in any time frame that matters. The question the discovery would force, with an urgency that no previous astronomical finding has generated, is whether we are going to take care of what we have while we develop the capacity to reach what we found. Let us be specific about what the current scientific evidence tells us about planets that might score near the top of the Earth Similarity Index. The TRAPPIST-1 system is the most studied collection of potentially habitable planets beyond our solar system. 7 planets orbit a small, cool M-dwarf star 39 light-years away. 3 of them, TRAPPIST-1, E, F, and G, orbit within or near the habitable zone. TRAPPIST-1e receives slightly less stellar radiation than Earth does from the Sun, roughly the amount Venus would receive if Venus orbited a much cooler star. On the Earth Similarity Index, it scores around 0.85. Webb has been studying the TRAPPIST-1 planets systematically since 2022. Early results published in 2023 showed that TRAPPIST-1b, the innermost planet, appears to have no substantial atmosphere, at least no thick carbon dioxide atmosphere that models had predicted. This was a sobering result. It suggests that intense radiation from the host star, even one much dimmer than the Sun, can strip atmospheres from close-orbiting rocky planets. Whether TRAPPIST-1e has retained an atmosphere is still being investigated. The observations required are more demanding because E is farther from the star and has a longer orbital period, requiring more telescope time to accumulate enough transits for a reliable atmospheric measurement. The Kepler mission identified over 50 planets in the habitable zones of their stars, though many of these orbit M-dwarfs rather than Sun-like stars. The TESS mission Kepler's successor has continued adding candidates, including some around Sun-like stars at distances close enough for Webb and future telescopes to study in detail. The star Tau Ceti, about 12 light-years away, is one of the nearest Sun-like stars and has been a target of multiple planet searches. Multiple planet candidates have been proposed based on radial velocity data, though confirming rocky planets in habitable zones around Sun-like stars at this distance remains challenging with current instruments. Tau Ceti is slightly smaller and less luminous than the Sun, making its habitable zone slightly closer in, but it is close enough to Sun-like that any planets in that zone are genuine candidates for study. The star 61 Virginis, about 28 light-years away, has confirmed planets but none yet confirmed in the habitable zone. HD 40307, about 42 light-years away, has a super-Earth candidate in or near its habitable zone. The search is active, the candidates are accumulating. The Habitable Worlds Observatory, if funded and launched in the 2040s as the Decadal Survey recommends, is specifically designed to directly image Earth-sized planets around the 25 to 50 nearest Sun-like stars and measure their atmospheric compositions. Its primary mission is the detection of biosignatures. If a perfect Earth is within that distance range, that instrument would find it. The timeline from here to that capability is roughly 20 years for design and construction, assuming funding. Then years of observation to accumulate data. The discovery of a confirmed perfect Earth with atmospheric biosignatures could realistically happen sometime in the second half of this century. That is within the lifetime of people alive today. Now consider what the world looks like at the moment of that announcement. Consider the political and cultural context in which a finding this significant would land. Science has been wrestling for decades with how to communicate findings about the search for life elsewhere. The problem is that the public responds to definitive claims and the science produces probabilistic ones. A headline that says scientists find possible signs of life on distant planet is technically accurate but generates a very different response than the underlying data warrants. Previous candidate biosignature detections, a possible phosphine detection in Venus's atmosphere, potential methane variations on Mars, have generated enormous coverage followed by the slow erosion of certainty as more careful analysis revised the initial results. A confirmed biosignature on a confirmed Earth-like planet around a confirmed Sun-like star would be different in kind, not a possible detection. A confirmed one verified by multiple independent measurements across multiple telescopes, reviewed by the scientific community across months or years before public announcement. The kind of finding that does not fall apart under scrutiny because the scrutiny has already been applied. The announcement protocols for such a discovery do not currently exist in any formal sense. Unlike first contact with an intelligent civilization, which has been the subject of formal protocols and working groups through organizations like the International Academy of Astronautics, a purely atmospheric biosignature detection has no established response framework. Who announces it? In what venue? What language is used? What follow-up commitments are made? These are not trivial questions. The framing of the announcement would shape the public response. Discovering life elsewhere changes nothing about the physical conditions on Earth. It does not make climate change more or less real. It does not alter the economics of renewable energy. It does not fix supply chains or geopolitical tensions, but it changes the psychological and philosophical context in which those problems are addressed. A species that believes it is the only life in the universe has a particular relationship with its own planet. It is both the only life and the only home, which creates a certain kind of responsibility. but also a certain kind of cosmic isolation. A species that knows it is not alone, that the emergence of life is not a singular, improbable accident, but something the universe does when conditions allow, has a different sense of its own significance. Neither smaller nor larger necessarily, but different, more embedded in a larger biological reality. Whether that difference would translate into better decisions about how to treat the planet that actually sustains us is an open question. Human behavior is not obviously responsive to cosmic perspective. People have known intellectually for decades that Earth is a small planet in a vast universe, without that knowledge significantly redirecting human priorities. The pale blue dot photograph, taken by Voyager 1 in 1990, shows Earth as a fraction of a pixel in a sunbeam against the blackness of space. Carl Sagan's reflection on it is one of the most widely circulated pieces of science writing of the 20th century. And yet, but a biosignature detection is different from a photograph of cosmic scale. A photograph tells you that Earth is small. A biosignature tells you that the chemistry that produced life here is not unique to here. The second finding has a more specific implication. If life emerges wherever conditions allow, and if intelligence and technology emerge from life under sufficiently stable conditions and over sufficient time, then the question of what happens to a technological species when it destabilizes its own atmospheric chemistry is not hypothetical. Other examples may exist. The outcomes of those examples, unknown to us because of the distances and time involved, may include both survival and catastrophe. We would be one data point in a distribution we cannot fully see. That is a different and more pressing kind of information than a photograph showing we are small. The question of what we would do with the information depends enormously on what the information actually says. Let us consider a few scenarios. Scenario 1. The planet has biosignatures consistent with simple photosynthetic life. Oxygen, water vapor, trace carbon dioxide. No industrial signatures. The planet is biologically active, but there is no evidence of technology. No radio emissions detected in decades of searching. No atmospheric chemistry that requires intelligence to explain. This tells us that life is not rare, or at least not as rare as our current absence of evidence has allowed us to assume. It tells us that the chemistry of life generalizes across stellar systems. It does not tell us that intelligence is common. It does not tell us that civilization is common. It may in fact suggest that the transition from simple life to complex life to intelligence is the rare step, not the initial emergence of biology. This would be the most scientifically thrilling and practically sobering version of the discovery. Life elsewhere. Intelligent life, still only here. Scenario 2. The planet has biosignatures and radio emissions. Not directed communications, just the kind of radio frequency leakage that a technological civilization generates by existing. Television broadcasts, radar, communication signals spreading outward at light speed from the planet's surface. We have been generating this kind of electromagnetic signature since the early 20th century. Our own radio bubble extends roughly 100 light-years in all directions. Detecting radio leakage from an exoplanet would be extraordinarily difficult. The signal strength drops with the square of the distance, and the radio frequencies would overlap with natural astrophysical sources. Current radio telescopes, even the largest arrays, are probably not sensitive enough to detect Earth-equivalent radio leakage at interstellar distances. But the Square Kilometre Array, a massive radio telescope currently under construction in South Africa and Australia, pushes the boundary of what is detectable. Future arrays could push it further. If we detected radio leakage from a nearby system simultaneously, with the atmospheric biosignature detection, the combination would be definitive. Technological civilization elsewhere, not just life, not just intelligence in the abstract. A civilization generating the same electromagnetic noise we generate. The response to this discovery is genuinely difficult to model. The political implications alone would be enormous. Would nations respond cooperatively? Would the discovery be classified? Would private organizations attempt to establish contact independently of government channels? Would the knowledge destabilize existing geopolitical structures by providing a common external reference point that transcended national interests? History suggests that major disruptive discoveries do not produce neat, coordinated responses. They produce fragmentation, exploitation of uncertainty, competing interpretations, and gradually, over years and decades, a new consensus that integrates the finding into a modified worldview. The discovery of a perfect Earth with technological inhabitants would follow that pattern, magnified enormously. Scenario 3. The planet had biosignatures and industrial signatures decades or centuries ago, based on the light now reaching us. But those signatures have changed. The industrial markers have declined. The atmospheric chemistry has shifted toward a cleaner composition. The planet's civilization, if it still exists, has transitioned away from whatever was producing the industrial signatures. This would be the most directly instructive discovery for our own situation. A civilization that went through what we appear to be going through and came out the other side. Not through collapse, but through transition. The atmospheric chemistry would be the record of how that transition unfolded. We could not communicate with them in any time frame that mattered for our current decisions. The light we are seeing left that planet before most living humans were born. But the atmospheric record would tell a story we could read. A story about whether industrial civilizations can redirect themselves. Whether the chemistry of technological development contains a path through the destabilization phase to something more stable. Whether we are looking at a possible future or a historical exception. That information, even indirect and incomplete, would be among the most important data humanity has ever obtained about its own situation. Now step back from the scenarios and ask a question that sits underneath all of them. Why does the discovery of a perfect Earth matter to people alive today, given that we cannot reach it, cannot communicate with it in any meaningful time frame, and have no ability to act directly on whatever information we learn from its atmospheric chemistry? The answer is that the discovery would change the frame within which we understand our own circumstances. Not by providing practical solutions to the challenges we face on Earth, but by changing the context in which those challenges exist. We currently make decisions about our planet, our atmosphere, our resources, and our future under a set of implicit assumptions that are rarely examined. One of those assumptions is that we are unique. Not necessarily in the religious sense, but in the practical sense that the experiment of life and civilization has been run once, here. And we have no external reference points for how that experiment tends to go. Every decision we make about our own future is made in the absence of comparison cases. Finding a perfect Earth would give us a comparison case. Imperfect, incomplete, separated from us by years or centuries of light travel time, but real. A planet where the same basic chemistry that produced us also produced life. Where a star similar to the Sun also produced stable conditions for billions of years. Where a world similar in size and composition to ours also developed a biosphere, or did not, or developed one and lost it, or developed one and is still here. Each possible outcome tells us something about the distribution of fates available to worlds like ours. And knowing that distribution, even roughly, even imperfectly, changes how we think about our own position within it. A species that knows it might be one of many examples can ask different questions than a species that assumes it is the only one. Not better questions necessarily, not questions with easier answers, but questions that are grounded in a larger reality. The perfect Earth is a mirror, not because it shows us exactly what we are, but because it shows us that what we are is not the only version of what can exist. And that reflection, even from 20 light years away, even arriving as patterns in starlight filtered through an atmosphere we cannot visit, changes something fundamental about how we see ourselves. We have spent the entire history of our species assuming we are alone. Not everyone, not always. But our scientific understanding has been built on the working hypothesis that we are the only confirmed example of life in the universe. And everything that flows from that, our sense of responsibility toward this planet, our sense of our own significance, our sense of the stakes involved in the choices we make, collectively, has been shaped by that assumption. The discovery of a perfect Earth would be the end of that assumption. Not with a dramatic announcement that resolves every question, but with a measurement, a spectrum of light that carries information about a planet circling a distant star. And, within that information, the chemical fingerprint of something that should not be there by any process, except biology. The day after that announcement, the sun would rise at the same time. The weather would follow the same patterns. The political problems that seemed intractable the day before would still be intractable. Nothing about the physical world would have changed, but the context would have changed completely. And context, it turns out, is where almost all the important decisions are made. We are very likely not alone. The mathematics of planetary formation suggest that billions of Earth-sized planets exist in habitable zones throughout the galaxy. The chemistry of life, built on carbon, water, and a handful of fundamental organic reactions, is not special to Earth. The elements required are the most common in the universe. The conditions required are not so specific that they could not be reproduced elsewhere. We do not know this with certainty. We have confirmed nothing. We have detected no biosignature, no radio signal, no second example of any kind. We are still, as of this moment, the only confirmed instance of life in the universe. But the instruments that could change that are being built right now. The Habitable Worlds Observatory, the Square Kilometre Array, the Giant Magellan Telescope, the extremely large telescope currently under construction in Chile. These are not speculative future technologies. They are concrete projects with funding, timelines, and scientific teams. They are the hardware of a search that has been underway for decades and is now approaching the sensitivity required to succeed. The discovery of a perfect Earth is not guaranteed. The nearest Sun-like stars may not have Earth-like planets in their habitable zones. The planets that are there may not have atmospheres. The atmospheres may not carry biosignatures. We may search for decades with the best instruments ever built and find nothing that rises above the noise. But the probability that we are the only life in the observable universe is low, deeply low. The universe contains an estimated 2 trillion galaxies, each containing hundreds of billions of stars, most of them with planets, many of those planets in regions where liquid water could exist. The chemistry of life uses the most common elements in the universe. The timescales available are in billions of years, more than enough for evolution to operate. Something like us almost certainly exists somewhere. The question that remains open, the one that the Habitable Worlds Observatory and its successors are trying to answer, is whether something like us exists close enough for us to know about it in our lifetimes. If the answer is yes, everything changes. Not the physics, not the distance, not the challenge of reaching or communicating with another world across interstellar space. Those realities remain unchanged. But the way we understand ourselves changes. The story we tell about who we are and what we are doing here and what we owe to the planet that sustains us changes. The frame within which every conversation about our future takes place changes. That is what it means to find a perfect Earth tomorrow. Not a solution to our problems, not a destination to escape to. A mirror held up at an impossible distance showing us what we might be, what we might have been, what we might yet become. The light from that mirror is already traveling toward us. We just have not built the instruments sensitive enough to read it yet. We are working on it.